Here's an example, a typical example of what we're going to be doing in using Newton's law of gravity to solve problems. We've got a satellite that's orbiting the Earth at 225 kilometers above the Earth's surface. So we want to know what is its speed, what is the speed of its orbit, and what is its period. In other words, how much time does it take to circle the Earth one time? So we're going to use these equations that we just talked about to solve this problem. So use given, find, and solve, and draw a picture. Now here's the Earth. You can draw the continents and stuff if you want. I'm not going to. Okay. Now, actually, there are some things that you need to know. Now, our textbook has a table in it with the table of all the radius of the Earth, the radius of all the planets and the sun and the moon. Or you can just get on Google and just Google, what is the radius of the Earth in meters? Just Google that, because you need to know it to solve this problem. It doesn't give it to you here. But the radius of the Earth is 6.38 times 10 to the 6 meters, which is 6 million meters, which is 6,000 kilometers. It's about 4,500 miles in radius. It's big. Earth is big, compared to us anyway. Now, what is the mass of the Earth? Well, again, you can just Google, what is the mass of the Earth? And you'll find that it's 5.98 times 10 to the 24 kilograms. So even though this is that information is not given to you in the problem, you have to look it up. On a test or quiz, I'll give it to you though. Now, here's something to realize. This right here, this 225 kilometers above the surface of the Earth, that's the height above the surface. That's an altitude. That is not the radius of my orbit. On this scale, 225 kilometers is actually quite small. It'd be about right here. So if this is the radius of the Earth, my satellite is actually orbiting the Earth right about there. Not very far away from the Earth on this scale of the Earth. Most satellites, well, all satellites in low Earth orbit are actually very, very close to the Earth relative to the Earth. So, and so I'm going to call this H. H means our height above the surface. And I'm going to change this 225 kilometers because it's in kilometers. What do we want it to be in? We want it to be in meters. So I'm going to call it 225,000 meters. And what are we trying to find? Well, we're trying to find our orbital velocity, orbital speed, I should say. And we're trying to find the period of the orbit. Okay, so I think we're ready to solve it. Well, let's start off with our basic equation here. This thing's in orbit, so it's moving in a circle. Okay, so the Earth's gravity is pulling on it. And so we know that the force of gravity is equal to the universal gravitational constant times the mass of the Earth times little m is usually the mass of our satellite, which wasn't given. If the mass isn't given, what can you assume is going to happen? It's going to cancel out. Right. Over r squared, that's what we learned. Newton's law of gravity. But it's moving in a circle, so this force is going to be equal to a centripetal force. I mean, the force of gravity is a centripetal force, and that's equal to m. And this is the mass of the object that's moving in a circle. And notice that that mass cancels out. One of the r's cancel out. And we're left with v squared equals this. So our orbital velocity is equal to the square root of g m over r. So it's very easy to derive. Now, if you could start here if you wanted. You could put this on your equation list and start here with the orbital velocity equation. Oh, this is going to be long. This is 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. I include the units, and so should you. 5.98 times 10 to the 24 kilograms, so mass of the Earth, divided by, oh, what is this r? Is it the radius of the Earth? It includes the radius of the Earth, but is our satellite at the Earth's surface? I hope not, because it's about to explode as it, vaporizes in the atmosphere. No, it's above the Earth's surface by this much. So what do we have to do to figure out what r is? Exactly. So the radius of my orbit is going to be the radius of the Earth plus my height above the Earth. So that's going to be 6.38 times 10 to the 6 meters, plus my height is 225,000 meters. The biggest mistake students make is they leave this in kilometers. You can't add kilometers to meters. Yes?
Can you make it a little bigger?
Okay. If this is in kilometers, you can't add it to meters. You have to change it to meters. Well, when you take your calculator out and do the math, this r turns out to be 6.605 times 10 to the 6 meters. A little bit bigger. One thing you could do is just move the decimal over 6 times, 1, 2, 3, 4, 5, 6, and call it 0.225 times 10 to the 6 meters. And then you can just add the 0.225 to the 6.38, and you'll get that, if you want. Or you can just plug it into your calculator. Now we can plug this value for r into there. 6.605 times 10 to the 6 meters. Now do this, okay? I'm going to show you the answer. Do it. Use your calculator and do it yourself, because if you don't get if you can't do it yourself, then there's no point. So when you plug all this in, you get your orbital velocity is equal to 7,770. I'm rounding off the 3 significant figures here. It's actually 7,771 if you do it in your, but I'm going to round that off. Meters per second. And that's my orbital velocity. How fast is 7,770 meters per second? It's fast. This is about 5 miles per second. If you do the unit conversion, this is about 5 miles per second. If you want it in miles per hour, it's about 17,500 miles per hour. It's bloody fast. Yeah.
So how many times do you think a satellite goes around the Earth in like a year?
How many times in a year? Well, we could figure that out. But first, let's figure out what the period is, and then we could answer that question. So now that we know the velocity, we can figure out the period, because the velocity is also equal to 2 pi r over the period. And so I can solve for the period. The period is equal to 2 pi r over the velocity. So the period is equal to 2 pi times r, which is 6.605 times 10 to the 6 meters, divided by the period, divided by the velocity, which is 7,770 meters per second. And notice that the meters cancel. You have 1 over seconds, which is in seconds. And you get a value of, when you round it off, and do this yourself, 5,350 seconds. That's a little over 89 minutes, which is almost an hour and a half. So that's equal to my period. Now let me zoom out. We'll go over the whole thing here again. Okay. When you're solving these problems, be very careful with units. And make sure that if they give you a distance above the Earth's surface, that's an altitude. It's not the radius of your orbit. You're going to have to look up the radius and the mass of the Earth. There's a table in your book, or you can use Google. Or you can write it down on an equation list. So it's always there for you to use. You apply Newton's law of gravity. If you're in orbit, the force of gravity is a centripetal force. You can easily solve for V, or whatever you're trying to solve for. When you plug in your numbers, please include units so that you can cancel things out. I didn't show you the units, how that works here. But it does give you meters per second. Make sure you add the radius of the Earth plus your altitude, and make sure they have the same units. This is actually a very low altitude for a satellite. This satellite won't last very long. It'll last a few months, maybe a couple of years before. There's a tiny bit of atmosphere up there. The space station flies at an altitude of about 400 kilometers, almost double this. Even there's a tiny, tiny fraction of the atmosphere that will eventually bring it down. So they have to boost its orbit every once in a while with rockets. Very, very small rockets. If you get up, several thousand miles into space, pretty soon there is absolutely no atmospheric drag anymore, and you'll essentially be in orbit forever. The moon, there's no atmospheric drag on the moon. The moon will be in orbit forever. And then, of course, you can use the fact that we're in a circular orbit to calculate the period of the orbit. And there you go. Any questions? Very good.